Hello. Good evening, everyone. How are you all? 1 second. Let me just check once. Good evening, everyone. First of all, okay. Yes. So we have to. Okay. Yes. Okay. So hi. Dodavida. Sorry, Akash. Can I call you Akash only? Hi, Nalin. Good morning. Good evening. Sorry. Good evening, Nalin. Okay. Good evening, Venkatesh. Hi, Pushpa. Hi, Lu. Hi, Anand. Hi, Tashmiya. Okay. So everyone is here, I see. Let's start. How's the Josh, guys? Hello, Aryan. Hello. I am good, Nalin. How are you all? How are you, Nalin? How is everyone? How is your day going on? Okay. So are you ready for today's class? Okay. I'll just place it here so that I can read your comments. Okay. So all normal. Okay. So normal is, I think, not bad. Okay. Unless you say it's going bad, then that means it's going bad. But normal is okay. Acceptable. Okay, my day is going good actually. Yes, because I get to see you guys. Yes, I get to talk to you guys. I get to learn with you guys. Okay, so yes. How is Pachapati? Okay, what about the rest of you? What are we doing today? So today we will be solving the most repeated PYQs, which we are doing every day, for hydrocarbons and haloalkanes and haloarenes. So yes, we are going into PU1. One is PU1, one is PU2, right? So we are going into PU1 chapters from now on. Next live will totally based on PU1. Okay. So yes, become prepared. I think we'll be doing equilibrium. We'll be doing. Let me just check what topics we'll be doing in the next class. Okay. Today we will be doing hydrocarbons and haloalkanes and haloarenes. Okay. For the next live, what are we doing? Yeah, in the next slide we'll be doing equilibrium, redox reactions and DNF block element. Okay. So today let's focus on haloalkanes, haloarenes and hydrocarbons. Okay. So let's start, shall we? Hi, Varsha. If I forget by mistake I didn't say anyone's name, I do acknowledge your highs and good evenings. Okay, so please don't take it to your heart. Okay, sorry, sometimes I'm not able to see all the comments. My net may be working a little slow. Okay, so let's start with haloalkanes and haloarenes first, then we'll go to hydrocarbons. Okay, yes, let's start. How's the Josh, guys? Yes. Okay. So it's basically organic chemistry, right? So if your concepts are strong, we will be able to answer them. Okay. Yes, you will be able to answer them. Okay. The organic compound. This is the organic compound. What it can be classified as. So let's see the organic compound first. What do you think it is? Benzyl halide, aryl halide, alkyl halide, allylic halide. Okay. What do you think it is? Okay, so see, this organic compound we are talking about, majorly which kind of bond we are dealing here? We are looking at this bond. This CCl bond. We are looking at this CCl bond. Okay, what do you think is the relation here? What kind of halide is this? Is it a benzyl halide? Is it an aryl halide? Is it an alkyl halide or allylic halide? Okay, simple. Right? So see, when we are talking about benzyl halide, what is benzyl halide? When the carbon that is attached to the halide is connected to a benzene ring. When the carbon that is attached to the halide is connected to the benzene ring, that is benzyl halide. So by that approximation, it is an aryl halide. No, it is not an aryl halide. This is a benzyl halide, because where is the halide connected? To the carbon which is connected to the benzene ring, right? When we talk about aryl halide, so in aryl halide the arrangement is like this. The halide is directly connected to the benzene ring. The halide is directly connected to the benzene ring or the aryl compound. Okay, so in that case, this is an aryl halide. This is a aryl halide. Okay, then if we talk about alkyl halide, obviously alkyl halide, it looks similar to alkyl halide, right? But it is not, okay? So alkyl halide, any alkyl group will be there. I normally write it like R, okay? Any alkyl group will be there, and that will be directly connected to the halide. Allylic halide, very easy. We have double bonded carbon. Adjacent to that carbon, a carbon adjacent to a double bonded carbon, right? Carbon-carbon double bond, and to this carbon, to this adjacent carbon, the halide group is attached. If to this carbon the halide group is attached, that is your allylic halide, okay? So we have allylic halide, aryl halide, alkyl halide. Correct answer is A, yes. That is your benzyl halide. The answer is benzyl halide. This compound is benzyl halide. Okay? Okay. So Pranavi A, Venkatesh B. Why B? It's not aryl. This is aryl. When we talk about aryl, the carbon is directly from the ring, right? It's the ring that is attached to the halide. That is aryl halide. Okay, Pooja A, Pooja Darshan, Sanjana, Purvik. I had a student named Purvik when I used to teach. In my class, I had a student named Purvik. Okay. Hi, Pooja. Good evening. A, correct. RX 100. Okay, Ilu A. So all of you answered A. Okay, we're good to go. Let's move on to the next question. The correct IUPAC name of this compound. The IUPAC name of this compound. Hello, Advik. Okay, what should be the IUPAC name of this compound? So you need to try a few combination here. Okay, you need to try a few combination here. We have three substrates. We have three substituents actually. Fluorine, 3 to 5, C2H5, ethyl group, and nitro. So we need the locants. We'll try all the combination and then we'll see which combination fits the best. Which rule? We are looking for the lowest locant rule. Lowest locant rule. So whichever combination will have the least count, lowest locant, that will be called your IUPAC name. That will be your IUPAC name. C, third option, A. Purvik answered A. Nalin answered third option. So A, C. So most of you are answering C. Why, dear? Why C? Let's see. So let's start with, I'll start with the, what do you want to start with? Let's say I start with nitro first. I'll name nitro 1. Let's say if this is 1 and I go this side, this is 2, this is 3, this is 4 and this is 5. So that means 1, this is 2 and this is 5. That is one combination. Okay. Now if I start from, let's say, ethyl, I want the numbering from ethyl. I start from ethyl 1. So I see from this side it's longer, right? I'll go from the other side. 2, 3, 4. So in this case, if ethyl is 1, fluoro will be 4 and nitro will be 3. Okay, now last combination, what can be there? I'll start the numbering from fluoro. If I start the numbering from fluoro, 2, 3, 4. So I get 1, 2 and 4. Now see, which of the following follows the lowest locant rule? Let's start. How do we start it? From here, what do you get? 1, 2, 5, right? 1, 2, 5. So all of you are answering C actually. Okay, let's see. What do you get here? 1, 3, 4. Okay, here 1, 2, 4. Which has the least count, lowest locant rule? Which follows the lowest locant rule out of these? Let's see. 1, 2. 1 is similar. Okay, 1 is same for all of them. So obviously we are not distinguishing on the basis of 1. 2, 2. This one is out, right? Because 3 is obviously greater than 2. This is out. We are not naming according to this. Okay, now in between these two, we have 5 and 4. Which is lesser? 4, right? So that means this one numbering is correct. This is the lowest locant rule. This follows the lowest locant rule. This is the least count. This is the least count. Okay? Clear? So all of you who are answering C, fluoro, the naming would start from fluoro. Again, we have fluoro F, ethyl E, and nitro N. First will come E, then F. So you'll start with 4-ethyl, then 1 fluoro, then after that nitro. After fluoro, nitro will come. 2-nitrobenzene. These all are your substituents, okay? So they will follow the lowest locant rule. Which combination? Lowest locant rule. So we wrote 3 combination, giving numbering 1 to each of the following individually. Whichever gave us the lowest locant, we use that nomenclature. We use that to write the correct IUPAC name. So the correct answer is A. Yes, the correct answer is option A. Hi Joe. Okay, so now everybody answered A. Okay, Ilu, you answered C. After that, Ilu, okay. Why you sad? No need to be sad. Okay. Good evening, Vijay. Okay, Ramana. NEET class, Madi ma'am, please. NEET class, we are focusing on KCET for now. But if there is a possibility for NEET class in the future, we'll talk about it. Okay. Hi, GS World. Hi, Joe. A, yes, RX100, correct. Rekha also answered A. Hina, Pooja, Venkatesh, Darshan. Understood. Sumit also answered A. Okay, so now we are on board with A, not C, right? C will not be correct, right? Why? I know some of you might have gone like this, that no ma'am, nitro is there now, so the nitrobenzene will be there. We'll start the numbering from 1 only, right? That is the correct explanation. And 3, 4, 1, 2, 3, 4, 5. Yeah, that is correct, no? But that is not the correct answer. Why? Because we need to check for the lowest locant. So, in these kind of questions, little bit, like what you call it, little bit small level of knowledge, you know, your total concept clarity is required. If you have the total concept clarity, you will be able to answer these kind of questions. Which all chapters today? So Joe, you haven't read it. Haloalkanes and haloarenes and hydrocarbons. Haloalkanes and haloarenes and hydrocarbons. So PU1 and PU2. We are mixing today. Okay? Yes. So let's move on to the next question. Next question. Just a second. Read the question. Okay. Yep. A pair of compounds having the same boiling point. Same boiling point. So boiling point, again, whenever we talk about boiling point, we talk about intermolecular forces, right? If the intermolecular forces are strong, the boiling point will be high, and if the intermolecular forces are weak, the boiling point will be less. Clear? So which among the following have the same boiling point? That means same level of intermolecular forces are there. We have cis-butene and trans-butene. Okay, so let's draw. For this one, it doesn't work, I think. Okay, let's draw cis-butene. If I am drawing correctly, this is cis-butene and this is trans-butene. Okay, so do they have same boiling point? No, they do not have same boiling point. They do not have same boiling point. Why? D. So in this case, all of you are answering correctly. Yes, D is the correct answer. But why? For in between cis-butene and trans-butene, there is a difference. What difference is there? This is more symmetrical. This is this is more symmetrical actually. 1 second. Yes, in this one we differentiate on the basis of polarity. Cis has more high polarity. Okay, in this one the charges are opposite, they cancel out. Okay, so in this case there is no polarity, but due to high polarity, this have high boiling point. Cis isomer will have a high boiling point due to its high polar nature, high polarity. Okay, then we have N-hexane and neohexane. So N-hexane is simple, now normal hexane, CH3, CH2, 4, CH3, and in neo we have like this, CH3, and 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay, so here you can see the difference is on the basis of branching. This is a straight chain alkane and this is a branched alkane, and for branching, whenever branching is involved, the boiling point will be lesser. Why? Because the surface area is less. It boils off easily. Like, okay, so in this also the sequence is this will have higher boiling point. Benzene, naphthalene, again this is benzene, 1 ring. In naphthalene we have 2 2 rings. Okay, again this will be having higher, this will be having higher boiling point than benzene. This will be having higher boiling point than benzene. Okay, so that means the only answer is this. Why? Because these are enantiomers. These are enantiomers. That means they are non-superimposable mirror images of each others. They are non-superimposable mirror images of each others. So do they have same boiling point? Yes, because that means they only differentiate on the way they rotate the plane polarized light. Apart from that, all the physical properties, melting point, boiling point, density, refractive index, all these properties are same for them. Okay, they only differ on the way they rotate the plane polarized light. Okay, so that means, does this question depends on the structure of the compound? Yes, it does. Actually, you need to know what is, if we are talking about cis and trans, so cis has higher boiling point than trans. Okay, also structure involves here, because when branching is involved, boiling point decreases. Whenever branching is involved, boiling point decreases. So the correct answer is option D, which all of you, my dear kids, answered it. Yes, so all of you answered D. Actually, unitely you decided, and yeah, I think you all know the answer. Pooja, Shankar, Venkatesh, Sumit, RX. Okay, all of you are answering correctly. Aryan also answered. Darshan, Varsha. Okay. Yes, so let's move on to the next question. 1 second. Okay, the arrangement of the following compounds in the increasing order of their boiling point. Increasing order of their boiling point. Again, bromomethane, bromofoam, chloromethane, dibromomethane. I have given you the compounds. Again, very easy. In between bromine and chlorine, which is heavier? Bromine. So bromine will have a higher molecular mass, thus higher boiling point. Okay, so obviously least boiling point will be of what? This compound. This compound. So check for the least option, which has the third as the least. This one. This one. That means this is the correct answer. Third will have the least boiling point. Highest will be for the one which has the highest number of bromines. So that is your 2, bromofoam. So 2 is the highest, then 3 is your lowest, and in between 4 and 1, in between 4 and 1, as 4 has 2 bromines and 1 has only 1 bromine. Yes, you are shouting C. Okay, I saw that. Understood. Okay. So C, Shankar C, Nalin, Ilu, Shankar, Aryan, RX 100, Sonika, GS World. Some new faces I've seen. Okay, I take normally the live in the morning, but yeah, today I'm seeing some new faces. Anuj C, Vijaya C. Okay, Sonika also C. So every one of you is answering C. So you agree with the argument, right? Yeah. Okay, so see, very simple. In between bromine and chlorine, bromine has a higher molecular mass, thus it will have a higher boiling point. Okay, and then obviously this will have the least one, so you just figured out from one only. You didn't have to check for all of them. Okay, Darshan, Rekha, Shinchana. Now your name is Shinchan. Yeah, Shinchan. Okay, so next question. The organometallic compound Grignard reagent. This is a Grignard reagent on reaction with D2O, deuterium oxide. This is like water, but instead of water, hydrogen we used its isotope, which is deuterium. Okay, so we have this compound. We have this compound. This is a Grignard reagent, RMgX. This is a Grignard reagent, RMgX. And when Grignard reagent reacts with, one second. Okay, so when Grignard reagent reacts with D2O, I can write it like this: D positive, OD negative, right? H positive, OH negative. Isn't it similar to that? Nalin, that's not an answer. A, B, C, D. Wow. Okay, so everyone is answering A, C, D. You guys are also confused. It's okay. So you know this is Grignard reagent. Grignard reagent, it is a very strong base. What it is? It is a very strong base. What do bases do? What do your bases do? So my dear students, remember that bases abstract a proton. What do bases do? They abstract a proton. Their only goal is for looking for a proton. They provide an electron to a proton. Okay, you have base, you have nucleophile. They differentiate on the basis of the reaction. Okay, so nucleophile do what? They provide electrons to a electrophilic species, the species that is electron deficient, that is nucleophile. Bases, they do abstract a proton. What do you mean by abstraction of proton? They provide electron to hydrogen. They provide electron to this proton, H positive. They provide electron to H positive, then they are called bases. Nucleophile provide electron to an electron deficient species. Okay, there is the difference. Okay, so for bases, this is a strong base. What it will do? It will abstract a proton. Now what proton we have here? D positive. This is the proton we have here. So what will happen? Here this is negative, this is positive. Here this is negative, this is positive. Similarly here positive, negative. Similarly, you know the reaction, right? Negative will attack on this positive. This negative will attack on this positive. Okay, what will happen? There is a bond formation. I'll write here. There is a bond formation between carbon and deuterium, D. Rest all the bonds are same. Clear? Plus Mg OD Br. This is your final product. So how many of you? Third option. Nalin, you can't answer A, B, C, D. C. Now everyone is answering C. Yes, the correct answer is option C. Why? Because this is highly reactive. It's an organometallic compound. That means there's a carbon and metal bond involved. There's a bond between carbon and a metal. That means they are organometallic compound. Okay. Grignard reagent is an organometallic compound. It is a very reactive compound and also a very strong base. What do bases do? They abstract proton. From what? They abstract proton or they provide electron to a hydrogen ion, H positive ion. Okay, so that's what bases do, right? That's what bases do. They are electron donors. Okay, right? So here a bond will form between carbon and this deuterium, and we will get this compound, that is 2-deuterio-2-methyl propane. 2-deuterio-2-methyl propane. So the correct answer is option 3. C. Third option. Correct. Once again explain, ma'am. Okay, no worries. So we are given an organometallic compound. This one, organometallic compound. This compound is an organometallic compound, right? This is given to us. We are asked what will happen if it reacts with D2O. What is D2O? H2O, right? But in place of hydrogen, we have used deuterium, right? We have used deuterium. Deuterium is an isotope of hydrogen, okay? So D2O also will have D positive and OD negative, D positive and OD negative, right? Now, this Grignard reagent is a very reactive compound, first of all. Second thing, it's a very strong base. And what do bases do? They abstract a proton. Bases abstract a proton, or in other words, you can say that bases donate electrons to H positive. Bases donate electrons to H positive. So what it will do? It will donate electron to H positive. In this case, H positive. In place of H positive, we have D positive. Hydrogen only, right? But a higher mass hydrogen, okay? Isotope of hydrogen only, okay? So what will happen? Again, this in between this carbon and magnesium, metals are positive, electropositive. This is electronegative. Why? Because it is a non-metal. It will have a negative charge. This will have a positive charge. Here, D positive, OD negative. This negative will attack this positive. This negative will attack this positive, right? And we will get, there will be a bond between this carbon and deuterium, and MgODBr. The other compound, the byproduct will be MgODBr. That's how the reaction will happen. So yes, there are options which will confuse you. The bond can be formed between OD and this, but since it's a Grignard reagent, in a Grignard reagent, carbon is nucleophilic. This carbon is nucleophilic. This is nucleophile. It has negative charge on it. Okay. So here it will be behaving as a nucleophile. Okay. Thus it attacks the proton, H positive. which means it is D2 positive and D positive in this case. Okay, I hope it is clear. Joe, your question is up above. Can we come to conclusion to Grignard reagent? Yes, obviously. No. Not just MgBr. It will be like this. An alkyl group will be there, and alongside this you will have RMgX. This is the common formula for Grignard reagent. An alkyl group will be there, and you have Mg connected to a halide group, connected to a halide atom. That is your Grignard reagent. You can draw a conclusion by seeing that. Okay, done. Yeah, but just remember one thing, because this concept has been used in multiple questions. Grignard reagent, very reactive and a strong base. So that means it wants a proton. It wants to abstract a proton. Okay. What do nucleophiles do? They donate electrons to electron deficient species. What do bases do? They donate electrons to a proton. Okay. Now let's move on to the next question. Joe, I hope I answered your question. Okay. Next question. Which one of the following chlorohydrocarbons readily undergo solvolysis? So in solvolysis, what kind of reaction is solvolysis? Add any solvent, right? You are adding any solvent. What kind of reactions are solvolysis? Nucleophilic substitution or electrophilic substitution? So solvolysis is D for this one. Readily undergo solvolysis. D, yeah? A. So when we talk about solvolysis, what kind of reaction is solvolysis? It's when a nucleophile. It's a nucleophilic substitution reaction. It is a nucleophilic substitution reaction. You know, right, how do we get the names of reactions in organic chemistry? Right, whatever compound is coming, whatever kind of atom is coming, right, on the basis of that we name the reaction. If a nucleophile is coming, nucleophilic substitution. If it is getting added, nucleophilic addition. If an electrophile is coming, electrophilic substitution. If it is getting added, electrophilic addition reaction. So here the solvent is nucleophile. It provides electrons. Okay, so what is happening here? The nucleophilic substitution reaction will happen here. So for nucleophilic substitution, if a nucleophile is coming, the compound should be a very good electrophile. The compound should be a really good electrophile. Okay. Now, which among the following is a really good electrophile? It is which among the following is a really good electrophile? Hello Prajwal, good evening. C or D? So when we are talking about electrophile, which will have electrophile, right? That means positive charge. Okay, now see, I want you to imagine one thing here. If I remove this halide, what will be here? CH2 positive with this ring. Okay, if I remove the halide here, positive and a double bond. Okay, if I remove, by any chance I remove this, firstly it's very impossible, near to impossible to remove this, but if by any chance I remove this will be this phenyl cation, right? And if I remove this, then it will be here like this. Which of these carbocation is the most stable? There's your answer. Which of among the following carbocation is the most stable? That will be your product. That will undergo solvolysis. That will undergo nucleophilic substitution. Electrophile. Electrophile means it is electron deficient. If they are able to maintain this positive charge on them, if they are able to stabilize this positive charge on them, they will be able to react far more easily than these species which are not able to stabilize that positive charge. How does stabilization happen? Carbocation, right? Carbocation is getting formed. Oh my god, you have so many different answers. A, B, C, D. Some of you answered D also. Okay. Which is the stablest carbocation? This is what? Benzyl carbocation, right? Benzyl carbocation. This is what? not benzyl exactly. It's a primary one. It's a primary carbocation. This carbon is connected to only one carbon. It's a primary carbocation. Here, this is a phenyl cation. Everybody knows phenyl cannot, the benzene ring cannot hold a positive charge on it. Cannot hold a positive charge on it. This is phenyl cation. This is what? Vinyl cation. Vinyl cation. This is a double bond, already electronegative. It wants to snatch all the electrons towards itself, and you have one positive charge here. It's highly destable, highly unstable, highly unstable. 1 degree. What stability is there? Is there any resonance you can see? No, there is no resonance. Here, yes, there is resonance. Here, how can you see? I'll let you see the resonance actually. So here, let's see, like this. After loss of the halide, it will be like this, right? How do you stabilize it? This double bond will move this side, this bond will move this side, this bond will move this side. There is a resonance involved here. There is a resonance involved here, and due to this resonance, this carbocation is the most stable. If this carbocation is the most stable, it will undergo nucleophilic substitution reaction easiest. It will undergo the nucleophilic substitution reaction the easiest. So yes, you should. Why are you so doubtful? A, B, C, D. Which is the stablest carbocation? The stablest carbocation will give the nucleophilic substitution reaction. So here the answer is option A. Option A. Okay, let me see. Hi Pradhani, I think. Nalin is not sure. Venkatesh thinks B. Shinchan, finally A. Yes, correct. Hamshika, hi Hamshika. A. GS World Darshan. Good evening. Okay. You guys have doubts. Hi Him. Okay, so yes, you need the basic. Now we can see you need the basic because this chapter is not related to hydrocarbon, but carbocation is being used here. The concept for carbocation is being used here. Shankar A, Prajwal A. I hope it is clear, right? Now you can see it's not stable. Okay, first one more thing, just to clear you, what is happening here actually. It has these lone pairs. So here these lone pairs are delocalized. These lone pair of electrons are delocalized. That means it is not a single bond, it is a double bond. And I think everybody has cleared you till now that double bond is far more difficult to break than a single bond. Far more difficult. Similarly, here also there is resonance. These electrons are delocalized. There is resonance. So that means there is a partial double bond character here. Again, this is very difficult to break. At normal condition, it won't break. You'll need to give extra energy to it. Okay. If it is so difficult to break the reaction, will the reaction happen? No, na. And went with B except a resonance. My bad. It's okay. This one, it looks like that, but do you see any resonance here? If this by chance it becomes like this. Let me draw the bonds. Do you see any resonance if by chance if you're thinking this like this? So will this electron, there will be a double bond here. Any further than that, do you feel like any resonance will happen? The bonds will not move out of the ring. No, they will be in connection with the ring only. They won't go away from the ring. That's not how resonance works. Okay. CH2 and CH2, what would happen? In B option, if the bond was between CH2 and CH2. Yes, in that case resonance can happen. Yes, because there is a double bond. What is the condition for resonance? You should have a double bond, single bond, then double bond. In that case, resonance can happen. Yes, so if there was a double bond in between those, then there was a chance that this resonance could happen, because then this bond will satisfy this valency and this bond will go that side. In that case, resonance can happen. Okay, so you need a double bond, single bond and double bond, alternating double bonds. Then resonance can happen. Okay, why it can't be C? As I told you, it's a vinyl halide. Okay, so in this case the double bonded carbon is directly connected to the halide. So what happens here, this Cl has lone pair of electrons. These lone pair of electrons are in the resonance. So if I donate this here, this double bond will go here. What will be the resonating structure? I'll get CH2. 1 second, CH2 negative, single bond, CH, double bond, Cl, positive. Okay, so there is a double bond here between the carbon and the halide, chloride. There is a double bond. Is it easy to break the double bond? When you are doing solvolysis, you are substituting this halide with a solvent. We are substituting this halide with a solvent. Do you think this bond is easy to break now? Now it's a double bond. No, right? So there is a partial double bond character due to resonance between this halide and the other carbons. Okay, so yes, this vinyl cation also not stable. Why? Because double bond has which hybridization? sp2. That means it is electronegative, right? Firstly, it is electronegative. Electronegative means ability to attract electrons. It wants to attract electrons. Instead of that, we are giving it a positive charge. We are giving it a positive charge. It is already electron deficient, and on top of that we are adding a plus also, right? So it's like I already don't have any money, and on top of that I'm adding loan to myself. So it's like that. I'll be highly unstable, right? Stable carbocation, electrophile. Yes, stabler the carbocation, the easily it will go under nucleophilic substitution reaction. The stabler the carbocation, easily it will undergo nucleophilic substitution reaction. Okay. Ma'am, in B option, I think I answered it. Okay. Okay. So can we move on to the next question? Hi, Praneeth. Okay. I hope, yeah, this is basic hydrocarbon stuff. It's okay. Some of you might have doubts about resonance, how to draw resonating structures. Not so much to remember. You just need to remember a few facts that I know. Whenever there is a double bond, it is highly electronegative, right? Means it needs electrons. Okay, it needs electrons, and on top of that one I am adding a positive charge to it. So will this be a stable carbocation? No, it won't be a stable carbocation. Plus you know that sequence, right? Tertiary carbocation is more stable than secondary, then primary, right? And then we have benzoylic cation, which is more stabler than that benzyl cation. Only that sequence is more than enough to remember. You don't have to remember so many things. Okay, this is the detail that I should know because I am teaching you. For you, you should just know the sequence. Okay. Yes, next question I am going. Good evening, Nagraj. Next question. Okay, next question. Pradhani, Joe. Yes. Okay. Next question. Identify the products A and B. Very easy. You can identify it when we use AgCN and when we use KCN. What shall be the product? So very easy. When you have AgCN, this is a covalent compound. This is a covalent compound. This is a covalent compound. That means the bond between silver and carbon is the covalent bond. Okay. So here, when halide leaves, so we have only one possibility. This carbon is already involved in bonding with silver. It's not able to donate its electrons to this R group. Why? Because it will be positive, it will be negative, right? When halide leaves, X negative, right? The alkyl group will have the positive charge. So here, as the carbon is occupied by silver, this will not be able to donate its electrons, right? But nitrogen do have electrons. Nitrogen do have a lone pair of electrons, right? So it will donate the electrons to this R positive, this alkyl carbocation, and the bond will form between the alkyl group and NC. From the nitrogen side, the bond will form. From the nitrogen side, the bond will form. 1 second. See? Ayo, see? See? Seriously, see? Both are same. C and CN. See? At this point, I think you guys are just rage baiting me. Okay? Yes, it's a name reaction. It's one of the important one here. Okay. This is the reason for AgCN. Now here we have K positive and Cn negative. That means electrons are available from carbon and nitrogen. Both have electrons to donate. So which will form bond? Birch reduction. I'll explain Birch reduction, don't worry. Okay, so which bond will form? We have one possibility from carbon side and the other possibility from nitrogen side. We are forming bond with what? Carbon only, right? We are forming bond with carbon. So is carbon-carbon bond stable or carbon-nitrogen bond stable? Carbon-carbon bond is much more stable. Why? Because we already know that because we already know that carbon is such a versatile compound. It has property tetravalency, it has this catenation, right? So carbon forms bond with carbon rather strongly. Okay, so this will be the bond formation. What will happen in this case? Carbon will donate the electrons and we will get RCN. RCN. So first A will be, how many of you answered A? Honestly, how many of you answered A? It is an example of nucleophilic substitution reaction. It is an example of nucleophilic substitution reaction. Correct. Okay, so when you have different type of this table in your book, right, where different nucleophiles are given and you have the product that are getting formed. So there, this is one of them. This is important one. Okay, questions being asked. A. Now everyone is answering A. Wow. Venkatesh, Tanjiro. Oh, Tanjiro. Nice to meet you. Shankar, Diya, Joe. Joe is laughing. Hi, Tanjiro. Joe, A. Correct. Nalin, Venkatesh, Anant. Okay. Good. Let's move on to the next question. See, some of you answered C actually. I was laughing because both are same. Do you think both will give the same product? Then why bothering asking question? Why giving two reactions when we know already the product is? I can't see. Him, don't do that. Can't see. So as I told you, in AgCN the bond is covalent. AgCN is a covalent compound. Okay. So there is a bond between silver and carbon, that is a covalent bond. Okay. We have two possibilities. Either carbon can donate, nitrogen can donate. But since it is a covalent compound, this AgC bond is quite strong. Okay. Carbon is not able to donate its electron. Why? Because it is covalently bonded to silver. So who will donate? Nitrogen will donate. So that means the bond will form from the nitrogen side. So A will be RNC. Okay. KCN, the story is different. Why? Because KCN is an ionic compound. When you have an ionic compound, that means it is present as K positive and Cn negative. So here we have two possibilities, carbon and nitrogen. Carbon can also donate, nitrogen can also donate, which will form bond. Now the bond is forming between R and this Cn. R and Cn. R is an alkyl group, means carbon is there. So carbon-carbon bond is much stronger, or carbon-nitrogen bond? Carbon-carbon bond. So we have two possibilities. Either carbon can donate, nitrogen can donate. But since the carbon-carbon bond is more stronger, the bond formed will be in between carbon and that alkyl group. RCN will form. Okay, RCN will form. I hope it is clear. Okay, who asked me to explain again? That comment is gone, I think. Okay, Hema answered. Yeah, Hema asked why I can't see. So that's why I can't see, because this is a covalent, this is an ionic compound. The bonding is different. Okay, Hema. Sorry, your name is Hema, right? Not Hema. Okay. Let's move on to the next question. The major product of this following reaction. The major product of, okay. The major product of this following reaction. This is a simple reaction, right? Very simple reaction. But the answer is not simple. B. So fast. So fast you guys are. Okay, let's see. So we have this alkenol compound, right? We have a double bond and alcohol. Alkenol. You guys are not good in organic chemistry. I can see that. You guys have so many doubts. Okay. Okay, let's see. CH2, double bond, CH, CH2, OH. So when we treat it with HBr, what is HBr? H positive, Br negative, right? We have two possibilities here. What do I see? I see two possibilities here. First is here, this Br can add to this double bond. This Br can add to this double bond, right? Second possibility, something can happen here. Instead of OH, we can have the Br. Okay, both of these possibilities can happen. So which will happen and which will not? Which will happen and which will not? So yes, as most of you are answering B. Hi, that's nice actually. Only Nalin. Oh, that is Nalin spamming. So yes, both possibilities will happen. Both of them will happen. Why? Because HBr is in excess. If it is present in a limited amount, one product will form. Which one? The OH one. What happens here? As OH, this is a good base, it will abstract a proton. It will abstract a proton, right? And we will get this CH2, CH2, double bond CH, CH2, OH2 positive. It abstracted a proton, this OH negative, abstracted a proton, right? OH2 positive. Now this is a very good leaving group. OH2 positive is a very good leaving group. Oxygen already have a positive charge. It is highly electronegative, can't bear the positive charge. It will leave. When it will leave the bond, this will have a positive charge. Now this will have a positive charge. Br is negative. It will attack this CH2 positive. We will get CH2 double bond CH, CH2 Br. This is the compound form if only one HBr equivalent was there. If only one HBr equivalent was there, then this product will form. Okay. If you have HBr in excess, then will the reaction stop here? No, the reaction will go further on. We have one more possibility and extra HBr. Alkene, alkyl halide, not halide, hydrogen halide. You can say it hydrogen halide. Which rule we have? No peroxide. No peroxide. Which rule? Markovnikov rule. Markovnikov rule. Markovnikov rule. What is Markovnikov rule? That when a nucleophile or halide, when a negative species, or you can say nucleophile or any halide, okay, let's keep it simple, nucleophile. When a nucleophile is added to a alkene, when a nucleophile is added to an alkene, the nucleophile gets added to the more substituted carbon. The nucleophile gets added to the more substituted carbon. Nucleophile gets added to the more substituted carbon. This is followed only when you are doing nucleophilic addition reaction for over alkenes. For alkenes only this rule is applicable, to the more substituted carbon. So here we have carbon 1 and carbon 2. This is, let's say this is carbon 1 and this is carbon 2. Which is more substituted, carbon 1 or carbon 2? Marco Jensen, that is not Marco Jensen, that is Markovnikov. Markovnikov. Okay. B, A, B. Some of you changed your answer now. So nucleophile gets added to the more substituted carbon. Which is the more substituted carbon? 1 or 2? 1. Yes, the carbon 1 is more substituted. Why? Because one hydrogen, one group is hydrogen and the second group is this CH2Br. That means it is more substituted, right? More alkyl groups are there. Here we have only two hydrogens. So addition will be happening at carbon 1. Where the addition happened? Carbon 1. Okay. So I'll draw the product here. We will have CH3. The hydrogen will add to the other carbon, right? CH, Br, CH2, Br. Simple. Which is the answer? Option A. Option A. Yes, option A. Clear? Okay, good. Yes, Prajwal, the carbon 1 was the more substituted carbon. Yes, so the correct answer is option A. Clear? Not much is there. If only one equivalent was there, the product would have been this one, B, right? If only one HBr was there. But we have HBr in excess. That means lot of HBr is there. That means the reaction will not stop at this point only. It will go further on. Markovnikov addition will happen. Nucleophile will get added to the more substituted carbon. In this case, the more substituted carbon was carbon 1. Okay. So addition happens at carbon 1. And this is our final product. Okay. Go to next question. Yes, cleared, done. This was easy, you were answering wrong the first, the first person was answering wrong. Which of the following halides shows highest reactivity towards SN1? SN1 reactions: substitution nucleophilic unimolecular or unimolecular nucleophilic substitution reactions. Unimolecular nucleophilic substitution reactions. Okay, so now tell me which will have the highest reactivity. We look for certain things. What things we look for when we are dealing with SN1? First, this is a two-step reaction. Two-step reaction. It involves the formation of a carbocation. It involves the formation of carbocation in first step. It happens with retention of configuration. Okay, we get two products. As carbocation is a planar species, the attack can happen from either side, from back side and from the front side. Okay, so what happens here? We can either get we get both retention plus inversion product. Retention plus inversion product. Okay, so here one factor is there. And what kind of solvent we need? What kind of solvent we need? Order of reaction is 2 actually. 1 second. No. Order of reaction is 1. Order of reaction is 1. For SN2 it is 2. For this one it is 1. Inversion, configuration, and then we have the kind of solvent, polar protic solvent. Polar protic solvent. Here, on what quality are we distinguishing here? We have carbocation quality. Which quality? Carbocation. What is this? Primary carbocation. Primary, right? This is a primary alkyl halide. This is a primary carbocation if this Cl leaves. Similarly, here it will also be a primary carbocation. This is phenyl cation. This is phenyl cation. The reaction doesn't happen very easily with this one. Okay, so only one possibility is this one. This is a benzylic carbocation. Benzylic carbocation. So which is the most stable carbocation? Now all of you are answering correctly. Yes, carbocation is the answer. Yes, oxy, Hina. No, Hina A. No, oh, A is not the correct answer. Tanjiro answered D. Yes, that is the stability order, right? Benzylic are even more stabler than your tertiary ones. Okay, so the correct answer is option D. Yes, oxy, correct. Shinchan, carbocation. First, yes. It's a first order reaction. Yes. D. Yes. C. Shankar C. Rekha D. Aryan. Correct. Okay. So all of you are answering correctly. Now let's move on to the next question. In this reaction, the number of possible isomers for the organic compound X. Again, we have a Grignard reagent, RMgX, a Grignard reagent, treated with a primary amine in this case. You just need to remember one thing, what? That your Grignard reagent is a strong base. Your Grignard reagent is a strong base, and when strong base is there, what does it do? It abstracts a proton. So in this case, the proton will be abstracted from this primary amine. Okay. Yes, in this case, the proton will be abstracted from the primary amine. So what will happen? I'll just draw it. This has positive charge and this has negative charge, right? In CH3NH2, this has positive charge and this has negative charge. Okay, so just negative, positive, negative. This negative will abstract proton here and this negative will attack here. We will get what? Hydrogen plus clear? Yes, so the correct answer is this compound X. Okay, we need to find how many isomers are possible for this compound. What is this compound? This compound is this, right? CH3, C, CH3, and one more carbon we have, CH3. This is the compound, right? Okay, I'll draw it a little clearer for you all. so that you can tell me how many isomers are possible. This is 2-methyl propane. 2-methyl propane. That means it is an isomer of what? Butane. This is an isomer of what? Butane. Butane has how many isomers? This is an isomer of butane. 2-methyl propane. Only 2 isomers are possible for this one. Only 2 isomers. 2-methyl propane, this is one. The second one is N-butane. The second one is N-butane. Okay, only 2 isomers are possible. First is this 2-methyl propane, second is N-butane. Okay. So the correct answer is option A, C, B, C, B, C. Only 2 isomers. You see any other isomers being happening? Nope, only 2 isomers are possible. Is there any stereoisomers? Is there any geometrical isomers? No, because no double bond is there, no cis trans isomerism will happen. Okay, then stereoisomers also not possible, right? Because we don't have any chiral center. All the groups are same. Okay. Yes, so the correct answer is C, and only Tanjiro answered C. Rekha also answered C. Taran, B. It's okay. Okay, the correct answer is option C. Only 2 isomers are possible. Okay. Okay. Now, array. 1 second. There are so many comments I missed. C, C. It's me extreme. So if you have if you are solving PYQs and topics with hints, so if you have concept clarity, if you know PU1 and PU2 chemistry throughout, okay, basically the PU2 chemistry is more important for your KCET. So if you are confident that you will be able to solve all the questions, and you are able to solve all the questions, that means you are doing the PYQs and you are able to solve all the questions, doing the mock test, you are getting a really good score of 40, 50, above 40 you are getting. That's actually a really nice score. Okay, then yes, that will be more than enough. Okay, but if you are not sure about your preparation, then macha, there is a problem. Okay, so if you are sure that you have the correct knowledge and you are able to solve the question, then solve the questions as much as you can. Okay, solve the questions. Okay, that will be enough. C, 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 correct. Okay, Mohammed, thumbs up. C, 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 2. Okay, done. Next question. Which of the following halides undergo hydrolysis on warming with water aqueous NaOH? Hydrolysis is happening. We are given water and aqueous NaOH. Water and aqueous NaOH. D. Firstly, tell me what is the kind of type of reaction that will happen. If you have an halide here, let's say RX, I'm writing any halide I have, and it is treated with water and aqueous NaOH, what kind of reaction is it? As in, okay, 1 second. Just try it. Answer first this one. What kind of reaction is this? Okay, let's see. Nucleophilic substitution reaction, right? Nucleophilic substitution reaction. This halide will get substituted. Okay, I will answer your doubts after this question, don't worry. Okay, so that means this halide group will get substituted by OH here, right? Yes, water here actually. Okay, so what will happen? This is a reaction. What kind of reaction? Nucleophilic substitution reaction. Nucleophilic substitution reaction. Now see, which among the following will go the nucleophilic substitution reaction faster? All are aryl halides, right? All are aryl halides. But ma'am, you said aryl halides have a double bond character, right? They won't undergo nucleophilic substitution reaction. This bond is not easy to break. It has a double bond character, right? So a very interesting thing here, we have electron withdrawing groups. NO2 is an electron withdrawing group. Okay, this electron withdrawing group withdraws the electron from this ring, from this halide. This electron withdrawing group withdraws the electron from this group as well as the halide. Okay, so if it is removing the withdrawing the electrons from this bond also, that means it is withdrawing the electrons from this bond also. That means this bond is weak. That means this bond is weak and easy to break. This bond is weak and easy to break. Okay, so in that case, if any other nucleophile comes, this ring is already electrophilic. Why? Because these nitro groups are withdrawing the electron density. These nitro groups are withdrawing the electron density from this ring as well as this halide. This ring as well as this halide. Okay, so that means this ring is already electrophilic. It doesn't have much electron density. So what it will go? It will, like when the nucleophile attacks, it will undergo the reaction easily. It will undergo the reaction easily. Normally, when you are reacting any aryl halide with a nucleophile, the reaction does not happen under normal condition. You either have to apply too much pressure, you will have to apply too much temperature or something. Okay, generally the reaction doesn't happen. But if you substitute lots of electron withdrawing group to the ring, what happens in that case? These electron withdrawing group withdraws the electron density from the ring as well as from the halide, this CX bond also. Okay, so this CX bonds become weak, it breaks off easily, right? And the substitution reaction happens. Second, this ring became highly electrophilic. Why? Because all the electron density is being withdrawn by these nitro compounds, these electron withdrawing compounds. Okay, so in that case, if any nucleophile comes, the reaction happens rather quickly. Okay, so which will have the highest, which will be undergoing hydrolysis? Only this one, option D. Okay, D. How many of you answered D? Okay. Okay, now let's answer your doubts first, then we'll go to the next question. Sorry. Okay. Alpha Sol. I struggle with organic chemistry every time, either it's in board or KCET. Will it be helpful if I just see the KCET series? Also, please tell organic chemistry weightage out of 60. So, if you are scared of organic chemistry, I know it looks scary because your concepts are not clear, because you didn't study well in PU1. Okay, so if you purchase the series, if you have the series, that will help you, that will provide you a systematic way of studying. So let's say if you have any doubt in theory, you can watch the theory lectures. If you have doubt in any PYQs, all the PYQs questions are being solved there. You can check the video and solve all the PYQ questions alongside. Okay, that is one advantage you have. Okay, second thing, even if you take the series but you do not practice the questions, if you do not practice the questions, then it is not going to help you. Okay, nothing can help you in that case. Okay, even if you are scared of organic, at least focus on 4 or 5 chapters. I'll tell you. Focus on alcohol, phenol ether, aldehyde, ketones, carboxylic acid, amines and biomolecules. At least finish these 4 chapters, because in KCET they have a much higher weightage. Obviously you won't be able to score 60 out of 60 because you are skipping chapters, but even if you are bad in organic chemistry, just do these 4 chapters. Learn. If you have learned already, do revision, then solve questions. Okay, in series you will find everything there. Every chapter is given there in a systematic manner. You have DPPs, you have PYQs. Okay, so it's a very nice and organized way of studying if you're starting last minute, because you don't have the time to sit and look for the resources and then figure out which chapter to study, which chapter not to study. Okay, we are here to help you. Okay, so if you can do that, that's very good. Okay, but don't skip organic chemistry, it's not optional. Okay, are there any master stroke videos of yours covering? Actually, SSY, Aishwarya ma'am has covered all the topics, all the chapters from PU1 and PU2. So no, I don't have any master stroke videos. Okay, sorry about that. Yeah, I came pretty late for you. So for now, I'm just your doubt solving ma'am and the question solving ma'am for you. Okay, okay. Ma'am, in KCET we should solve the questions beside of that only. It is true or fake? Prajwal, ask exactly what is your question. I can't understand your question much. Sorry. Ma'am, in KCET we should solve the questions beside of that. So I don't know what you're asking. Rough sheet you're asking, or as in, please reframe your question. Okay, aqueous KOH. Okay. The double bond, organic chemistry is tough, alpha sol, I feel you. Organic chemistry is tough, but with practice, with having an open mindset and thinking that I just need to study it for the last, I think you're not appearing for your second boards, right? You're not appearing for that, so I just have to study it till 24, then I'll be done. 23 I have exam, I'm done. Okay, so you think of like a freeing mindset, then maybe you will be able to focus on it more. Okay, never get the answer. In organic chemistry, you don't ever get the answer. Just, it's okay. With the practice, you'll come. Learn from your mistakes, okay? Because it's not the final exam yet. You can make mistakes. You can correct those mistakes. You can learn from those mistakes. And do not repeat those mistakes in your final exam, because the final exam is still far away, okay? Still days apart. I love physical chemistry, okay? For me, physical chemistry is the safest zone for me. Physical chemistry, inorganic chemistry, I love, okay? Organic is also something that was tough to deal with me, but yeah, yours is very easier actually. Yes, basic doubt. Yes, Nalin, ask your doubt. Okay, if we have stretched and written the right answer, will they give marks in boards? Scratched and written, obviously. So Shreyash, if you have written the correct answer, but if you did like this, Macha, they won't give you answer, no. They won't give you mark, no. Because you already, even if you did it correctly, but you did this, no. That means you thought it was wrong for you, right? So no, sorry for that, but yeah, they won't be getting any marks if you did like this. But if some part is getting like this, they might consider it, okay? Okay. From physical chemistry. Okay, from physical chemistry we have chemical kinetics, solutions, सबसे पहले solutions, chemical kinetics, solutions, electrochemistry. What else we have? Let me think. Only 3 chapters we have: chemical kinetics, solutions, electrochemistry. Am I forgetting something? Think. Oh, no, Prajwal. Okay, that is fake, obviously. If you're solving the questions, you're given the sheets and all, solve the questions there, okay? And you just fill the OMR sheet. Only that thing is going out, no? Only that thing will be checked by your examiner. The OMR sheet, no. You don't have to sit down and tick each and every answer. No. That is for you, no? Because whenever you're solving the questions, you won't be doing like that one question you solve, then you're filling the OMR sheet. No. What you'll be doing, you'll be solving all the questions, and then what you do normally to remember it, that for this question, A is the correct answer. You tick it, right? Because you want to fill that answer in the OMR sheet later on, obviously, okay? For that OMR sheet, you are ticking. If you want to circle or do anything, you do that, okay? You don't, it's not compulsory. It's what you do, okay? These chapters are important: chemical kinetics, solutions, electrochemistry. From physical, as far as I remember, only these chapters are there in your PU2. Okay, equilibrium is also important. Yes, equilibrium. Okay, what else we have? Thermodynamics and that thing is like not much of a weightage. Yes, Nalin, ask your basic doubt, bruh. 1 second. Arthi Kulkarni. So you struggle with aldehyde ketones carboxylic acid chapter. So do one thing, from that focus on the name reactions from your aldehyde ketones carboxylic acid, focus on the name reactions. For acids, the acidity order. For acids, the acidity order, the name reactions. Major thing that's been asked from these chapters are their method of preparation and chemical properties. Physical properties, 1-2 questions may come, may not come, but major is the method of preparation and their chemical properties, okay? From physical properties, acidic nature, the acidity they ask, okay? So these 3 things you can focus on and solve questions as much as you can, because sometimes you forget what you learned, but you will remember if you solved any questions regarding that. Questions are a very short way of learning anything, okay? So even if you are scared, even if you don't understand, just do these 3 things: method of preparation, chemical properties, and a little bit of physical properties, okay? And then solve questions from the last 10 years, 20 years. If you have any book, solve the last 10 years questions, okay? And then after that, you'll see that you are able to, this will become an easy chapter for you also, okay? And obviously, if you're not studied 100% of the chapter, you will not be able to answer 100% of the questions. So keep in mind that also. But if you're able to answer 80 to 90% of the questions, that's actually a very good sign. CH3, then story would be opposite. Then no reaction, nothing of this will happen. CH3 is an electron donating group. It will increase the electron density. It will, if in place of this we have CH3, if in place of this we had CH3, it is an electron donating group, right? It is electron donating. It will increase the electron density here. If the electron density is high, will a nucleophile attack? It's already high in electrons, and a nucleophile which already have extra electrons, it comes here. Will it attack? No. Repulsion will happen. No reaction will happen here. Okay. In that case, this might react. If you provide extreme conditions, this might react, but this won't ever react if NO2 is replaced with CH3. Okay. Obviously. Okay, Nalin, let me, how do you tick the answer, lol? Thanks. Oh, you're welcome. You're asking, I've done the video already, but it's okay. So we have from inorganic, we have coordination, very important. Okay, D and F block. Okay, what do we have from inorganic? What else we have? If these 2 chapters are very important, coordination, D and F block. Okay, let me think if I'm missing any other chapter. These are the high weightage chapters: coordination, D and F block from inorganic. S and P block is not there. So yes, next question. No, in that case, if none of these is the answer, then do none of these. But if this is there, then you maybe tick this one. All NO2 is replaced by CH3, then tick this one, okay? And if none of these is there, then tick none of these. Okay, next question. Okay, sorry, macha. Okay. Yes, okay. So practice well. Okay, there is no shortcut to your success. You still need to do the hard work. Okay. Next question. Are you ready? The compound having the longest CCl bond. Longest CCl bond. Yes, there will be revision for chapters. Don't worry. There will be revision for all the chapters. Organic, physical, inorganic. All chapter revision will be there. Okay. Okay. So tell me which will have the longest CCl bond. Longest CCl bond. What do we mean by longest CCl bond? Longest CCl bond. Okay, so when we talk about longest CCl bond, so we are looking for what thing? We are looking for, in terms of, okay, I'll ask you. Which bond is the strongest? Which bond is the strongest? So the strongest bond will be the one this one, because it has 3 bonds, triple bond. Okay, this is the strongest bond. Okay, then this double bond, then this single bond. This is in terms of strong nature, strong bond. If I talk in terms of length, which is the longest bond? Which is the longest bond? You'll say, ma'am, this one, right? Because the bond is weakest here. That means the distance between these carbons is actually far, right? The distance between these carbons is actually much, like they are very far apart from each other. So the bond length order will be this. Right? Clear? In terms of hybridization, this is sp3 hybridized, this is sp2 hybridized, this is sp hybridized, right? So in this case, the S character is the highest, 50% S character is there. Here we have around 33%. Yes, here we have around 25% S character. 25% S character. Now S character, what do we mean by S character? S is highly electronegative. One thing. Second thing, S orbital wants to be closer to the nucleus. It wants to be closer to the nucleus. There's a fancy name for it, that's called penetration effect. So S orbital wants to be closer to the nucleus. Okay, if it wants to be closer to the nucleus, that means it will be very close to the nucleus. The bond length will be very less. That means the bond is really strong. Okay, bond strong means length is very small. Bond strong means the bond length is very small. Okay, in terms of hybridization also you can figure it out. Okay. So here let's focus. Okay, for this one, what kind of bond is there in between C and Cl? Again, I know these electrons, it has 6, right? This will donate here, this will go this side. There will be resonance. There will be this go here, this go this side, this will go this side, this will go this side. There is a resonance. That means this bond has partial double bond character. Now let's move on to this one. Okay, in this case there is electron withdrawing group, right? Obviously it is withdrawing electron, so it is withdrawing electron from the ring as well as from the Cl bond also, right? That means the flow of electron is from the Cl to the ring. So that means there is also a double bond character here. Again I can write there is a double bond. Clear? For this one, again as I told you, vinylic, right? 1, 2, 3, 4. So in this case also the electron flow is like this. So that means here it is also a partial double bond. In all these 3 cases, there is a partial double bond character. What kind of bond is present here? Single. Is there any resonance here? Yes, we can do like this, but will there any other resonance? Will there be resonance possible for this one? For resonance, you need double bond, single bond, double bond. Double bond, single bond, double bond. Okay, if it is not there, there will be no resonance. So in this case, there is no resonance. Okay, so here the carbon and Cl bond is a pure single bond. sp3 hybridization. Okay, so which will have the longest bond length. This is the weakest bond. Okay, these are the stronger bond. This is the weakest bond. If it is the weakest bond, that means the bond length is the longest. Okay, correct? So that means the correct answer is option B. Why? Because it has sp3 hybridized carbon. Okay, the CCl bond is a single bond, purely single bond. Okay, so it has the longest bond length. Clear? If bond length is large, then compound will have longest CCl bond. Yeah, that is the same thing. If you can say bond strength is weak. If bond strength is weak, the bond length is really long. Okay, the bond length is really long if the bond strength is weak. There is one more relation, just to not to confuse you but to give you a little revision, that if you have bond order, you know bond order, right? Higher the bond order, higher the bond strength. So bond strength and bond order are directly related. Okay, so if you have, let's say if you have bond order 2 and bond order 3, then bond order 3 means the bond strength is stronger in 3 than 2. Okay, then obviously it is inversely proportional to the bond length. Bond length. Clear? Bond order is directly proportional to bond strength and inversely proportional to bond length. Bond strength is inversely proportional to bond length. Okay. 1 second. Yes, single bond, no resonance. Oxy answered correctly. Okay. Go for the next question. Okay. Let's go for the next question. BSB. What is BSB? Bond strength, bond length. Okay. The compound major product is, the major product will be. Arey, Meet Zafar, hi. So Meet Zafar, every one of our teachers know you now. Even bio ma'am know, bio ma'am, maths sir, physics sir. Yeah, we all look for you now. Good evening. Good evening. It's okay. So tell me for this one. Okay. Okay, one thing. Are you guys liking this session? Are you guys liking the session? You guys are not liking the session, okay? You guys are not liking the session. A, B, D. Wow, so variety of answers is coming. Yep, definitely you're not liking the session. Okay, so let's answer this question first. When we are doing, what is this, halogenation in presence of UV light. When we are doing halogenation in presence of UV light, firstly we have two conditions: UV light, halogenation we are doing in presence of UV light or in dark. The mechanism is totally different. The reaction is totally different. What is the difference here? What is the difference here? So, in case of UV light, if you are doing, what kind of reaction happen? Addition. The reaction that happens is addition. Why? Because UV light is there. That means energy is there. If energy is there, you can break the bond and new bond can form. If too much energy is there, UV light means sunlight, energy is there, right? So if too much energy is there, you can break any bond and add any compound, add any atom. That means addition reaction will happen. Okay. What is the mechanism we have here? Radical addition mechanism. The mechanism that follows is radical addition mechanism. Okay, so here what is happening? In place of substitution, what is happening here? Addition is happening. Okay, so here what happens here? So do we have any possibility here? Okay, addition happens here. Okay, now in case we have dark, if we are doing the reaction in dark, so obviously not much energy is there. So in that case only substitution happen. In that case only substitution happen. Okay, simple. We'll need this after few questions. That's why I'm explaining it now, so that you can answer there correctly. Yes, I know, because I normally take live classes in the morning. You guys are in the evening batch, I think. You take in the evening. Okay. Yes, my name is Ekta. I'm your Ekta, ma'am. Ma'am, crying, please. I'm not crying. Oh my God, I'm not crying. I'm just laughing. It's like every time I have to remind you to like this session. I'm not crying, obviously. Why I'll cry for likes? It's okay, but thank you for the concern. How do you remember me, ma'am? I remember you because you are there in my every live and you answer the questions. That's why I remember you. And every other teacher look for your name because you answer and you ask really nice doubts. Okay, that's all. Okay, so here, if the reaction is happening in presence of UV light, so we have two possibility. Firstly, addition reaction, basically radical addition reaction will happen, right? So we have two possibilities here. What two possibilities, ma'am? We have 1 and 2. These two possibilities here. Okay, so either radical formation will happen on this carbon 1 or radical formation will happen on this carbon 2. Okay, because if we are going from radical mechanism, that means Br radical will get added to either this radical or this radical. Okay, which radical will it get added to? Now let's look at the individual 1 and 2 radical. Let's look at them. This one is a primary radical. This one is a primary radical. This one is a benzylic radical. Benzylic radical. Which radical is more stable? Benzylic radical is more stable. Which radical is more stable? Benzylic radical is more stable. Okay. So reaction will happen at 1 or 2. The reaction will happen at 2, right? This possibility prevails. Why? Because see, I know you might be thinking, ma'am, why not the reaction happening at ring? Because this NO2 group is there. It is withdrawing the electron density from the ring, and because of that, the Br radical cannot attack on this ring. It can only attack on these two positions. Now here also, which radical is more stable, the product will depend on that. This is a primary radical, this is a benzylic radical, and we know benzylic radical is much more stable than a primary radical, right? Similar to carbocation. So if you don't remember, then you can relate radical equal carbocation. Whatever be the order for carbocation, that same order will be for your radical. Okay. So here, which products have this addition, this product, right? Product B. So the correct answer is option B, alpha sol A. Why? Center carbon is most stable. Yes, because it is a benzylic carbon. Okay. Okay, yes, so correct answer is option B. Correct answer is option B. Okay, so here one product is from A, because again it doesn't happen. Why? Because this carbon is primary carbon. This radical is primary radical. Okay. Okay, so next question. Tertiary alkyl halides is practically inert to substitution. Yes, because of A being less stable. Yes, the radical is much more stable, much less stable. If you make it a primary radical, that primary radical is less stable than a benzylic radical. Okay. Okay, now tell me the answer for this one. Tertiary alkyl halide is practically inert to substitution by SN2 mechanism because of. So when we talk about SN2, substitution nucleophilic bimolecular reaction, it is a one-step reaction, single concerted step. Clear? Okay. What kind of solvents prefer SN2? Polar aprotic solvents. And normally the order of, in terms of, you know, alkyl halides, if we are dealing with, the order goes like this. Primary is more reactive than secondary, and then tertiary. Why? The reason is simple, steric hindrance. The reason is steric hindrance, because in this reaction, in SN2 mechanism, the reaction happens in one step only. Okay, the the halide group leaves from the front side, and the nucleophile attacks from the back side. Okay, so if you have like this, the nucleophile attacks from the back side, and the halide group leaves from the front side. Okay, so it happens with inversion of configuration. Clear? Okay, so the reason is steric hindrance. Yes, very easy, steric hindrance. Option D. Clear? So how many of you answered D? D. A. Oh, Shrikant answered A. No, Shrikant. Yes, because of severe steric hindrance. Yes, this is the order, because of severe steric hindrance. Okay, so as all of you almost answered D, we'll move on to the next question. A haloalkane undergoes SN1 and SN2 reaction depending on. So which is the factor that determines whether a reaction will go by SN1 or SN2 reaction? Which factor we have? SN1 and SN2. SN1 and SN2. The class started at 5. Okay. So it SN1 and SN2. Solvent used in the reaction? Yes, because in SN1 we use polar protic solvent. Polar protic solvent favors SN1 reaction, and polar aprotic solvent favors SN2 reaction. Temperature affects the rate of reaction, not mechanism. These are your mechanisms. Temperature only affect the rate, not mechanism. Type of halogen atom, again leaving group ability. It will only work if you are dealing with SN2 or something, unless you don't, it doesn't matter what kind of halogen atom we have. The SN1 and SN2 only depend on the solvent we use. On the solvent we use. Option A. Stability of haloalkane, you think that, right? But does stability matter when we are talking about SN2 reaction? Does stability matter when we are talking about SN2? No, right? Why? Because stability of haloalkane only matters if we are talking about SN1. SN1, we are talking about a specific mechanism. But one factor on which both depends, SN1 as well as SN2, that is solvent, that decides whether the reaction will go by SN1 or SN2. Okay, that is secondary. This reason is secondary. Stability of haloalkane. If it is a good tertiary haloalkane, then obviously it will undergo SN1, and for primary doesn't matter. Okay, so the main reason is solvent. The main reason is solvent. Okay. Wood's reaction, okay, you need to figure out the combination of haloalkanes. You need to figure out the combination of haloalkanes. Now, as you can see, the kind of alkane that we are getting, it is not a normal one. It's not a symmetrical alkane, right? It is not a symmetrical alkane. We are getting this 2-methyl propane. We are getting 2-methyl propane. It is not a symmetrical alkane, okay? So, what is happening here? Not Woods, we are having cross-Woods reaction. What kind of reaction? Cross-Woods reaction. Okay. So, cross-Woods reaction, you need to choose 2 alkyl halides. You need to choose 2 alkyl halides. So, you can see this is the point of their contact. So, that means one alkyl halide will be this one. One alkyl halide will be something this one. And the second alkyl halide will be this one. Right. So, what are the 2 alkyl halides that you take? CH3Cl, chloromethane is 1, right? 1. Second will be something like this. The halide group will be on the second carbon. The halide group will be on the second carbon. So, let me see how many of you answered correctly. Good evening, ma'am. Good evening, guys. Gladys Lydia. What's your name though? New student. Hi, okay. Welcome to the class. Darshan C, A, B. It's still you're answering A, B, C, D. I've given you the answer. Chloromethane, right? And 2-chloropropane. Correct answer is option A. Option A. Yes, Rekha, correct. Pavitra, correct. Nagraj also correct. Good evening, Prajwal. Shrikant, A. Okay. So, every one of you answered A. Okay, so we can move on to our next question, I think. Okay. Do we have? No, we don't. So, actually, I'll be back in 5 minutes. Okay. Till then, just stay there. Okay. I'll come in 5 minutes. Can you explain again? I am new, madam. 1 second. Ali, Jafar, you want me to explain the last question? See, so we are talking about Woods reaction. So Woods reaction, we have 2 haloalkanes. They react with sodium in presence of dry ether, and we get symmetrical alkanes. That happens if you have a symmetrical alkane, right? But here this alkane is not symmetrical. We are getting an unsymmetrical alkane. So we use cross Woods reaction. Simple. In Woods reaction, you take 2 haloalkanes, treat them with sodium in presence of dry ether, and you get an alkane. The halogen group gets removed. Okay. So here this is the product we are getting. So what two haloalkanes will be here? We see there is one possibility, this one, right? And the other will be coming from this one. This should be our first haloalkane. This should be our second haloalkane. So first haloalkane will be CH3Cl, chloromethane, and second haloalkane will be this one, because there is a connectivity. This is the point of contact, right? There is a connectivity between the second carbon and this methyl group, right? So that means the halogen will be connected to the second carbon. The halogen will be connected to this second carbon. So if we connect something to this second carbon, we get 2-chloropropane. 2-chloropropane. Okay. So 2-chloropropane and chloromethane. These are your 2 haloalkanes. If you treat them with sodium in presence of dry ether, we will get CH3 plus 2NaCl. This is the final product you get. Okay. Okay, clear? Yes. So Mir Zafar, I hope your doubt is clear. Yes, I am going to take your revision. Okay, I'll be back in 5 minutes. Okay, thank you. I am from whichever state you want me to actually. But right now I'm in Karnataka state. Okay, I'll be back in 5 minutes. Okay. So I hope you guys were productive when I was gone. You guys were just chatting randomly. Yeah? Okay, let's start the class. Good evening. Okay, one of you asked good evening. Good evening, Amma Siddha. What's your name? Amma. Tuesday's board results. Yes, do let me know how did it go. Okay, I believe in you. I hope whatever you did will, make you succeed. Whatever marks you were aiming for, you get those marks. Okay, so let's start, shall we? Thank you. Okay, Tuesday is boards exam. So Tuesday is actually, yes, it's coming very soon. Are you ready, Mancha? Okay, everything fine. Everything is going to be fine. Okay, don't worry. Okay, so let's start. Everybody in the zone. Hi, Sandeep. No, you're not cooked. If you think like that, then maybe you are, but mid-May. Okay, so guys, everyone focus. Too much fun you had. Okay, enough of the fun. Let's start solving the questions. Alpha Sola. Yeah, you guys are funny. Hi, Akash. Hello guys. Hello Shrikant. Yes, you guys are still not ready for. Are you ready for this though? Are you ready for hydrocarbons? Huh? Hi Divyashri. Okay, please start. Yes. Okay. First question on your screens. You need to tell me which among the following is aromatic. Which among the following is aromatic? Again, do you know the criteria for aromaticity, or have you completely forgotten that? I believe you remember it, right? For aromaticity, we only have few criteria. For aromaticity, we only have few criteria. What are those criteria? Should be a cyclic compound. It should be planar. Should be conjugated. What else? It should have 4n plus 2 pi electrons. That means it should follow Huckel rule. It should follow Huckel rule. This is Huckel rule. Raya, I'm not from Bihar, and you definitely didn't see me there because I never been to Bihar. I do want to visit once, but I never been to Bihar though. Okay, you saw me in the wrong place. No, I came back from 5-minute break. Why are you talking like that now? I saw ma'am in Bihar. Maybe a doppelganger. Yeah, that could happen. Okay, so answer this question. Which among the following is aromatic? Aromatic. So for aromaticity, we have these 4 criteria. Cyclic, planar, conjugated, having 4n plus 2 pi electron. Having 4n plus 2 pi electron. Okay, so let's start from first one. It is cyclic, yes. It is planar, yes. It is conjugated, obviously it is conjugated. How many pi electrons it has? 1, 2, 3, 4, 5, 6. 6 pi electrons. So it is cyclic, planar, conjugation is there, have 6 pi electrons. That satisfies this? Yes, it does. Okay, so all the criteria are being fulfilled. That means this is a This is an aromatic compound. This is an aromatic compound. Let's move on to second one. For second one, is it cyclic? Yes, it is cyclic. Is it planar? That means it is lying in the same plane. Yes, it is lying in the same plane. Is it conjugated? Yes, it is conjugated. It is naphthalene. There is conjugation here, right? If you move this like this. Okay, conjugation is there. Okay, how many pi electrons are there? Let's calculate that. How many pi electrons are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. N equals to 2. N, if N is equals to 2, then you will have 10, right? 10 pi electrons. Follows Huckel rule. Follows Huckel rule. That means this is also aromatic. This is also aromatic. Now let's go here. Cyclic, planar, done. Cyclic, done. Planar, done. Conjugated, conjugated, yes, it is conjugated. There is some conjugation there, right? There is some conjugation there. Okay. How many pi electrons does it have? 4 pi electrons. How many? 4 pi electrons, right? If 4 pi electrons are there, does it follow the Huckel rule? Follow the Huckel rule? No, it doesn't follow the Huckel rule. So is it aromatic? No, it is not aromatic. What it is then? The species that is cyclic, planar, conjugated have 4n pi electrons. How many? 4n pi electrons. That is, what is that species? If it has 4n pi electrons, rest all the properties are same. Only the pi electrons are different. If it has only 4n pi electrons, that is called anti-aromatic. That is an anti-aromatic species. Okay, so this is not aromatic. Fourth, cyclic, planar, conjugated. All these are there. Cyclic, planar, conjugated. Now let's calculate the number of pi electrons. How many pi electrons? 1, 2, 3, 4. There is a lone pair also. There is a lone pair. 2 electrons are there. 5, 6. 6 electrons. Does it follow Huckel rule? Yes, it does follow Huckel rule. If n equals to 1, then 4n plus 2 will be 6. So yes, all the criteria are being fulfilled. That means this is your aromatic compound. This compound is aromatic. Now let's move on to this one. Cyclic, done. Planar, done. Conjugated, yes, it is conjugated because it has alternating double and single bond. Double, single, double, double, single, double, right? Okay, now see. Let's calculate the number of pi electrons. 2, 4, 6, 8. There are 8 pi electrons. There are 8 pi electrons. If there are 8 pi electrons, does it follow the Huckel rule? No, it doesn't, right? It follows this 4n pi electrons if n is equals to 2. That means this is not aromatic. It is anti-aromatic. It is anti-aromatic. Okay. So the correct answer is first, second and fourth. First, second and fourth. Option D. Option D is your correct answer. Okay. Good evening. App Patila, what's your name? 4n pi, yes, correct. 4n pi is followed. This is anti-Huckel rule. This is Huckel rule. 4n plus 2 pi electron, that is Huckel rule. 4n pi is your anti-Huckel rule. Okay. D, correct. Okay, so let's move on to the, yes, Nalin, correct, that will be your anti-aromatic. Okay, let's move on to the next question. Darshan, Aparna, Prajwal, Amma, Sid. Okay. Okay, good. All of you are answering correctly. Okay. Next question. What is the IUPAC name of this compound? IUPAC name of this compound. Deoxy, correct. Okay. Let's see. Identify the longest parent chain. Okay, so we'll start from here. 1, 2, 3, 4. If I'll calculate all the possibilities. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Okay. The longest parent chain consists of 4 carbon. The longest parent chain consists of 4 carbon. Now tell me what should be the name of this. Very easy, very yes, very easy actually. You can tell me the name. So 4 carbon. At 2 we have a methyl group. At 3 we have a methyl group, right? At 2 and 3 we have methyl group. So what do we say? 2,3-dimethyl. At 2,3, 1 second. 2,3-dimethyl. 2,3-dimethyl, 2,3-dimethyl. So it could be this, this and this. Okay, this can't be possible. That is not a name. Okay. Now, how many carbons are there? 4 carbons, bute. 4 carbons, bute. Wait, what is the position of double bond at second carbon? What is the position of double bond at second carbon? Bute 2-ene. Bute 2-ene. Okay. So that means YNE. That means triple bond. No triple bond. Incorrect. Butene, not the double bond is not at the first carbon. So obviously incorrect. Correct answer is option A. And how many of you answered option A? Aparna answered A, Hina answered A, Darshan answered A. A. Yes, Joe, Prajwal, Shankar, Rekha, Akash. Done. Okay. Okay, so yes, A, correct. So the correct answer is option A. Okay, so let's move on to the next question. Okay. The major product obtained when ethanol is heated with excess of concentrated sulfuric acid at around 443 Kelvin. Yes, Oxy, I understand. Yes, that is the correct answer. Okay. We'll explain the structure of methyl ethene. Methyl ethene, that is propene. No, methyl ethene is propene. Okay, so for this one, methyl ethene. So major product obtained when you have ethanol, CH3, CH2, OH. Okay, is heated with excess concentrated sulfuric acid at around 443 Kelvin. I'm talking 443 Kelvin. Okay, so what should be the product? Whenever an alcohol is heated with acid, what happens? Dehydration happens. What happens? Dehydration. Dehydration means loss of a water molecule. So here, how will the loss happen? I'll show you. CH3, CH, we have one H here, okay, and then OH, okay. Loss of one water molecule, this hydrogen and this OH, this loss happens, okay. Now 1 second, take pen. CH2, this goes here, then we have here H2 and H here. Yes, I drew it wrong. H2 OH. Okay, this is the compound ethanol, right? Dehydration means loss of a water molecule. OH from this carbon and hydrogen from the other carbon. This is a water molecule that got lost. Okay, it got lost. Okay, and there is a double bond to satisfy the valencies of both these carbon. There is a double bond that is formed between them. Okay, so this is the final product. What is this? Ethene. What is this? This is ethene. The correct answer is option C. Oh, why are you answering C? C, Rekha. Correct, Aparna. Yes, C. Okay, water molecule got lost. Yes, your water molecule got lost. C. So Vijay, now A, the answer is C. It's not ethane. We get ethene, alkene. When alcohol undergo dehydration, alkene is formed. Okay, alcohol undergoing dehydration, alkene is formed. Okay. And your sulfuric acid is a dehydrating agent. Sulfuric acid is a dehydrating agent. Okay. Done. Now let's move on to the next question. You need to identify A and B. What are the products A and B? What are the products A and B? 1 second. Yes, so what are the products A and B? First reaction is happening in presence of peroxide. So that means there will be peroxide effect will be observed, right? Peroxide effect is what? Kharsh effect. You call it as Kharsh effect, right? Right? Peroxide effect. Yes, peroxide effect, right? So in case of peroxide effect, your major product follows which rule? Anti-Markovnikov rule. Anti-Markovnikov rule. Anti-Markovnikov rule. Okay, so in presence of peroxide, the compound follows anti-Markovnikov rule. That means this halogen, this Br group will get added to the less substituted carbon. Br group, halide or any nucleophile will get added to the less substituted carbon. So in propene we have two possibilities. This is carbon 1 and this is carbon 2. Which carbon is more substituted? Carbon 2 is more substituted, right? But in presence of peroxide, we see peroxide effect. That means the rule that is used is anti-Markovnikov rule. In case of anti-Markovnikov rule, this bromine, this Br negative, it will get added to the less substituted carbon. Which is less substituted here? This one. This one have less number of alkyl group. This is the less substituted carbon. So for first A will be CH3, CH2, CH2, Br. Okay. This one also matches, this one also matches, right? So either this or this. Which will be the correct answer? For second one, when we are treating propene with HI, but there is no peroxide, then which rule is followed? Markovnikov addition. This is Markovnikov addition, right? In Markovnikov addition, what happens? The halide will attach to the more substituted carbon. Halide will get added to the more substituted carbon. That means carbon 2. If this is your product A, product B will be this one. CH3, CHI, CH3. This is your product B. Clear? Now, which option matches it? This one is following anti-Markovnikov rule, even when there is no peroxide. So this is not your correct answer. Nope, this is not your correct answer. What is your correct answer? This one question, D. Option is your correct answer. Okay, D is your correct answer. Yes, Markovnikov rule. Okay, how many questions are there? I believe there are like 10-15 questions, not much. D, 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 A. Okay. So yes, all of you are answering D now. Yes. Okay, D. Shrikant, not A, the answer is D. Why not A? Because this is opposite, right? These products are opposite. This follows Markovnikov rule. This follows anti-Markovnikov rule. But correct is here. In case of HI with no peroxide, Markovnikov rule is followed. And in case of peroxide, anti-Markovnikov rule is followed. Okay? Peroxide effect is this. Okay, I'll explain, don't worry. So peroxide effect is a very simple effect. In presence of peroxide, when you are doing addition of alkenes, in presence of peroxide, if you are doing addition of alkenes, the negative species, what we are adding? Negative species. Why? Because alkenes are electrophilic in nature. Alkenes are electrophilic in nature. If any nucleophile or any electron-rich species gets added to the alkene, you have two possibilities, right? One carbon will be more substituted, the other carbon will be less substituted. Substitution means alkyl group. More the number of alkyl group, more substituted that carbon is. Less the number of alkyl group, less substituted that carbon is. Okay. So in case of peroxide, in presence of peroxide, what happens? When you do addition of alkenes, when you add any nucleophile to alkene, that nucleophile will get added to the less substituted carbon. in presence of peroxide, when you do addition of alkene, the nucleophile will get added to the less substituted carbon. That is anti-Markovnikov rule or peroxide effect. Okay, that is simple, your peroxide effect. In presence of peroxide, the nucleophile gets added to the less substituted carbon. Here, this carbon has one alkyl group. This carbon has only 2 hydrogens. This is the less substituted carbon. So, when peroxide was there, the bromine got added to the less substituted carbon. Okay. Now, in case of here, HI, when HI is there, there is no peroxide. There is no peroxide. When no peroxide is present, absence of peroxide. Okay. What happens in that case? In that case, when you do addition of alkenes, the nucleophile will get added to the more substituted carbon. The nucleophile will get added to the more substituted carbon. Okay. Now, which of these is the more substituted carbon? Carbon number 2, right? So, the iodine will get added to the more substituted carbon, which is this carbon. And that's why we get the product D. We get the answer D. Okay? Clear? I hope you know the peroxide effect now. Very easy. Just remember peroxide effect, anti-Markovnikov rule. No peroxide or absence of peroxide, Markovnikov rule. Okay? Okay. Sure. Kalappa, I hope your doubt is also cleared. Why we get these products? Because of this peroxide, the product varied. Okay. Okay. Now let's move on to the next question. Shall we? Next question. Arrange the following in the decreasing order of their acidic behavior. Now here the acidic behavior will be directly proportional to what? The hybridization. The hybridization. Okay. So if I ask you, we have 3, SP, SP2 and SP3. These 3 hybridizations are there. Which is more acidic? Which is the most acidic, then medium, and then the least acidic? So as we know, this has 50% S character, this has around 33%, and this has around 25%. So what is exactly happening here? What is exactly happening here? Okay, so more the S character, more the electronegativity, more will be the acidity. Okay, more will be the acidity. So in this case, the sequence will be like this: SP, then SP2, then SP3. This is the decreasing order of acidic character. Okay, this is the decreasing order of acidic character. Very easy. We have 3 compounds: benzene, N-hexane, and we have ethyne. 3 compounds. Again, hybridization difference you can see. This is sp2 hybridized, this is sp3 hybridized, this is sp hybridized. So which will be the most acidic? Ethyne, then benzene, then hexane. Okay, so ethyne, benzene, hexane. Decreasing order will be ethyne, benzene, hexane. Ethyne, benzene, hexane. How many of you answered D? All of you answered D. Very good. Yes, sp is more electronegative, more acidic, thus more acidic. Yes. Okay, understood? Good. Next question. Peroxide effect is observed with the addition of HBr but not with the addition of HI to unsymmetrical alkene. Why? So for HBr and HI there is a difference. Why? Because the HI bond is much weak. HI bond is weak. If this bond is weak, when you break this bond symmetrically, you get I radical. If this bond is weak, if you break it, you get I radical, right? Now this I radical is not able to form bond with carbon radical. This I radical is not able to form bond with I radical. We are adding it to unsymmetrical alkene, right? Peroxide effect, right? You are adding it to unsymmetrical alkene. So there is a carbon radical involved there. Okay. So this bond is actually extremely weak. Extremely weak. Instead of this, what I radical do? This iodine radical combines with itself. One more radical of iodine, it combines with that. And this is the product we get, I2. We get I2. Instead of an iodine substituted alkane, we get I2. Okay, why? Because HI bond is weaker than HBr bond, and that iodine free radical combines with iodine molecules instead of this alkene radical. Yes, correct. B. Nalin, correct. B. Suresh said Darshan. Everybody is answering correctly. Sumit, Pavitra. Okay. Hina, Sharda. Okay, so the correct answer is option B. Next question. I need to do a few changes in this one. Till then you solve the, you can read, no you can't read the question. 1 second. Did I do something? Now tell me which is the final product. So if you treat benzene with chlorine in presence of, in dark, the conditions are dark, anhydrous AlCl3 in dark and cold, what happens? Substitution or addition? As I told you before also, in this case substitution happens. What happens? Substitution. That means these 6 chlorines will substitute 6 hydrogens, okay? Will substitute these 6 hydrogens that is present on the ring. Ring will still be aromatic. Aromaticity will be maintained. Aromaticity will be maintained. So, Macha, what should be the answer? Very simple, right? Yes, the correct answer is option A. The correct answer is option A. Option B does happen. Option B does happen. When does it happen? When instead of this condition you are given Cl2 added in UV light. In UV light you have so much energy. Instead of getting substituted, instead of doing this substitution, what happens? Addition happens, okay? And the ring will not be aromatic anymore. Okay? Good. Ma'am, what is this? This is hydrocarbons. We are solving questions from hydrocarbons. Yeah, I learned it from her actually. I didn't know what macha means. She told me. That's how I know. Okay. So A, correct. Correct answer is option A. Next question, 2-butene is reduced to trans-2-butene using. One of you was asking about this thing, Birch reduction. This is Birch reduction. Now what is Birch reduction? Very simple, very easy. What is Birch reduction? So when you have an alkyne, in this case you have 2-butene. When you have an alkyne and you treat it with Na, sodium in liquid ammonia, it gets converted into trans-alkene. Okay, so I'll just draw it. It gets converted into trans-alkene. This is trans-butene, right? Trans-butene. This is Birch reduction. This reaction is Birch reduction, okay? Sodium in liquid ammonia, that is your Birch reduction, okay? What is the reaction happening here? When you have any alkene, if you treat it with sodium in liquid ammonia, it gets converted into trans-alkene. Alkyne getting converted into trans-alkene, okay? That is your Birch reduction. One more reaction is there. If I want cis-alkene, then if I want cis-alkene, then I'll use this reagent. H2 in PD, palladium and carbon, okay? H2 in palladium and carbon, that is the catalyst I'll use. This do cis-alkene, okay? This is anti-addition, and here it is syn addition. Okay, now H2 nickel, it won't convert it into alkene, it will convert it into alkane, straight away to alkane. Na in liquid NH3, yes, that is our correct answer, okay? Now this one, obviously, it is used to convert into cis-alkene, okay? Zinc in dilute HCl, this is a reagent that is used to convert alkyl halides into alkanes. It converts alkyl halides into alkane. So obviously this reagent is not used. This is Birch reduction. Okay. Any alkyne when treated with sodium in liquid ammonia, it gets converted into trans-alkene. Okay. Hexachlorobenzene. Yes, hexachlorobenzene. Yes, Shrikant. Ayo, why D? Shrikant, the answer is straight in front of your eyes. The answer is B. The correct answer is option B. Okay. 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 So now let's move on to the next question. Identify the following compound which exhibits geometrical isomerism. Geometrical isomerism, which will be what is geometrical isomerism? That cis-trans isomerism is your geometrical isomerism. Cis-trans isomerism is geometrical isomerism, right? Normally it is exhibited by alkenes. So obviously this and this will not exhibit it. 1 and 2, in between 1 and 2, you have butene. Yeah, it can exhibit. This is butene, but if you have but1ene, in but1ene, there are no cis and trans possible. Why? Because we have different groups. To this carbon, hydrogen and this group is attached. To this carbon, only 2 hydrogens are attached. So for cis and trans, you need same group on same side, cis, same group on opposite side, trans. Okay. So here, obviously, this also not possible. So only option is butene. It can exist as cis and trans. Cis and trans. Okay. A, not B. Yes, A. Correct. Next question. The reagent used for the following reaction. Which reagent is being used for the following reaction? Okay, let me just update you. Okay, so really are then 20 gets only. Okay, so the reagent that is used for this following reaction, this is an alkyne. Alkyne is getting converted into cis-alkene. Alkyne is getting converted into cis-alkene. Okay, this is cis. So in case of cis, which reagent we used? With hydrogen we used palladium and carbon. Palladium and carbon, because this converts what? Trans. This gives trans-alkene. Okay, this is complete reduction. It will stop up to alkanes. It won't stop here. The reaction will go up to alkane if you use lithium aluminum hydride. Nickel also will get alkane. So only reagent is palladium and carbon. Lindlar catalyst we call it, right? Lindlar catalyst. Okay. Okay. This reaction, the correct answer is option B. Good. Next question. N-propyl chloride reacts with sodium metal in dry ether. What is this reaction called? This reaction is Wood's reaction. This reaction is Wood's reaction. And if you have N-propyl chloride is treated with sodium metal in presence of dry ether, what do we get? Coupling will happen, right? Coupling will happen, right? 2 NaCl plus 1, 2, 3, 4, and there will be end at CH3. 1, 2, 4, 5, 6. What are we getting here? N-hexene. What are we getting here? N-hexene. So which is the correct structure here? Option A. This is Wood's reaction. Option A. Correct. I'll answer your doubt at the end of the class. We're just near. 2 more questions to go, I think. C. Yes, that is the correct answer. C. Slow, ma'am. Because this is Wood's reaction. We have already done it before. Yes, C. Wood's reaction, we have already done it before. Any haloalkane when treated with sodium in presence of dry ether, we get a symmetrical alkane. Okay. Cross Woods mean we are getting different alkanes we are using. Okay. Next question. Toluene reacts with halogen. What is the kind of reaction? Tell me. If you have toluene, it reacts with halogen, let's say X2, in presence of FeCl3. Ortho and para halo compounds. It gives ortho and para halo compounds. So means we get one this ortho plus para. What is the kind of reaction? What is the type of reaction? So here, this is an electrophile. The halogen here, this halogen X2 is an electrophile. So what is adding here? substituting actually. Substitution happening, right? This halogen comes and substituted the hydrogen present here, right? Substituted the hydrogen present here. So this is an example of electrophilic substitution reaction. Electrophilic substitution reaction. Good. Every one of you answered correctly. Okay. D. C. Dinakar, this is not C, this is D. Why? Because this species is an electrophile. If an electrophile is substituting, that means it is an electrophilic substitution reaction. Okay, the name comes from the this reagent. Okay, yes, D. Next question, for the preparation of alkanes, if we have an aqueous solution of sodium or potassium salt of carboxylic acid, if we have this, which method will make this? Which method? If you have done aldehyde ketones carboxylic acid, you already know that. You already know this. Hydrolysis. No. If you have sodium or potassium salt of carboxylic acid, the reaction is Kolbe electrolysis. Remember this reaction? Kolbe electrolysis. We synthesize symmetrical alkanes from it. At anode we'll get this and carbon dioxide, and at cathode we'll get hydrogen. At cathode we'll get hydrogen. Using electricity or electrolysis, we synthesize alkanes. We synthesize alkanes from aqueous solution of sodium or potassium salt of carboxylic acid. That reaction is Kolbe electrolysis. So we are using electrolysis. It's a very old question. So it comes in two categories. You can use it in hydrocarbon because we're talking about alkanes, and also in aldehyde ketones carboxylic acid because it is there. Kolbe reaction. Kolbe electrolysis reactions. Kolbe electrolysis reaction. Okay. Okay. I think we are done. Any doubt you have, I am here for 5 minutes. You can ask me. Okay. And if no doubts are coming, then the class is over. Thank you so much, and I hope you learned something from it. If you do learn it, do give it a thumbs up, do give a like, okay? And yes, if you have any doubts, if you didn't understand it, do mention them in the comments actually, okay? If you have right now, I'll answer them right now. If later on you're watching it, then you add it in the comment section, I'll respond to you, okay? 8th once again, okay? I'll explain 8th question. 1 second. Okay, so 8th question, 2-butene is getting reduced to trans-2-butene. Okay, so this is a very simple process. When 2-butene is treated with sodium in liquid ammonia, the reagent is the catalyst or the reagent we use is sodium in liquid ammonia. Okay, this is the reagent. We call it Birch reduction. Birch reduction. So what it does, it converts this alkyne. It converts alkyne to transalkene. Transalkene. Okay, what are we getting here? Alkyne is getting converted into transalkene. So that means the reagent is sodium in liquid ammonia. That is Birch reduction. Okay, this is also one of the method. Lindlar catalyst we call it sometimes. Hydrogen in palladium and carbon. Hydrogen in presence of palladium and carbon. Okay, so in this case the product is little different. In this case we don't get trans, we get cis-alkene. Okay, rest two methods are used for different kind of substrate. Okay, so that's why we did not consider it here. Okay, so when 2-butene is treated with sodium in liquid ammonia, we get transalkene. Okay, alkyne to transalkene. Simple. OMR based, Nalin. Are you not preparing for CT? It's an OMR based. You'll be given paper and then you'll have to fill the OMR sheet, solve the questions and OMR sheet. Tomorrow morning, okay, 1 second. 1 second. Okay. Pooja, this is the 8th question once again. KCET CBT OMR based. Okay. You're welcome. Tomorrow morning is not my session. My session will be on Saturday. Yes, Saturday. You need PDF of this folder. I think it will be uploaded to the WhatsApp channel. You can go in the description. It will be there. Okay. Phosgene is COCl2. This is phosgene. This is phosgene, COCl2. It's a very dangerous gas. Okay. Yes, it's a very poisonous gas. This is phosgene. Okay. There is no A. Answer A. Transbutene, cisbutene. Cisbutene has more higher boiling point. Why? Because cisbutene is more polar. Cisbutene is more polar than transbutene. If it is more polar, it will have a higher boiling point. Okay, you're welcome, Pooja. I think your doubt is answered. Okay, done. Good evening. So Darshan, if you have any doubt, please join the WhatsApp channel. It's there. The schedule is posted there only. Okay, you can check there, and the PDF will also be posted there only. Okay, you can download from there also. Okay. Okay. Yes, COCL2 correct. Okay, then bye guys. Bye Venkatesh. Bye. Okay. Yes. Okay. Take care. Bye bye. See you in the next class. All the best. Okay. Ta-da. Bye.